So thank you all for showing up. I know it is the middle of the summer. If it's okay with people, raise your hand. If it's not, I would like to take a picture of the crowd so that when I submit my expense report for a trip to my hometown, there's not too many questions coming back in. Are people okay? No objections? Cool. Well, just do this. Yeah, if you could look like this talk is going well. I find it's a lot better to do this at the start, because sometimes at the end people are like, nah, I don't know, man. But yeah, okay. I'm going to talk about ML pipelines with Apache Spark and a little bit about how to do them with Apache Beam as well. And it's going to be mostly in Scala. There is at least one Python example in there. And the APIs remain pretty much the same between the languages, which was a really interesting design choice. And for those of you who work in Python, I'm really sorry that our APIs look so much like Scala APIs. So yeah, my name is Holden. My preferred pronouns are she, her. It's tattooed on my wrist, which is really useful in the morning. Sometimes I'm a little hungover and I just don't remember where I am or who I am. I'm a developer advocate at Google. I focus on open source big data. This means that I mostly work right now on Spark and Airflow, but I've worked on other projects with different levels of priority as decided by our wonderful leadership team, which is of course always correct. You got that part on video. Okay, cool. Lovely. I'm also on the Spark PMC. This is cool. It means that if the Spark project wants to get rid of me, it is really, really hard. I like to think of it as like open source tenure, except it's kind of shitty because you don't get paid. So that's cool or not. Co-author of 2 books on Spark, and the third one, which I don't talk about anymore, it just pretend doesn't exist. And you can follow me on Twitter. I've started doing live reviews of code reviews. If you ever were like, live streaming sounds cool, I wonder how I can make it boring. You can come and join me and do live code reviews together. It's fun. I think it's neat. And I also have GitHub and other videos. In addition to I am professionally, I am trans, queer, Canadian, and I live in America. Don't hold that against me. Turns out I like money. And part of the wider community. And this isn't directly related to Apache Spark or machine learning, but I think it's really important for those of us, especially those of us who are going to be building machine learning systems, to embrace a more diverse community, because otherwise we're just going to build systems which reinforce our existing biases, but faster. And what I look for is not just faster existing biases. I like new happy software, which doesn't just make me sad. So come and join me and make stuff that doesn't suck, or not. So hopefully you're all nice. I was guessing that most people here are engineers. And by engineers I mean in the American term engineer, the broad tent engineering, not the the iron ring. That's it. I swear I am Canadian. So how many people here are in software engineering or software development of some type? Okay, cool. And I know there are some people who are not. Does anyone who's not a software engineer, and you don't have to, want to share what they do, what your background is?
Oh. Me or?
Yeah, that would be lovely.
Oh, no. Well, I started off a long time ago as a mechanical engineering technology, so
cool.
I guess I don't have the ring, obviously, but it's the college version. And
okay.
Mechanical engineering technology, so I got 2 diplomas.
Cool.
But later on I did GIS,
okay.
which is computers, but not necessarily computer programming or computer engineering.
Cool. And do you want to share? Or, I know you.
I'm a biomedical engineer.
Cool. Yay. Shiny. Okay. So, and was there anyone else who's not an engineer who wants to share what they do?
I'm a sales guy.
Okay. And
product manager. I work with a bunch of engineers that work with Apache Spark. So.
Oh, cool. Okay. Cool. Yay. Awesome. I am really curious. How many people here are already familiar with Apache Spark? That is a very high hit rate. Okay. How many people are not familiar with Apache Spark? Okay, cool. So I'm going to try and walk the line and try and provide something that's useful to both of you. If you find yourself zoning out and you're already familiar with Spark, just close your eyes for a minute, and I promise it'll get interesting again. And if you're new to Spark and something doesn't make sense, feel free to stop me and we can go into it some more. So what's in store for our adventure? We're going to talk a little bit about why we would train models with Spark rather than traditional systems like scikit-learn. or R. If you're a big data person, you know, your options for training your models are limited. You could downsample and train with classical tools. You could use MapReduce and wait a few weeks. Or you could use Spark and have an interesting experience with lots of stack traces, but at least very fast. And for small data people, it's perhaps less important. Like, you don't have to use Spark. But if you want to do like really interesting explorations of like parameter spaces, you can do that a lot easier on top of Spark rather than just renting one really big compute machine from my employer, who will of course rent the best compute machines. Okay, and even if you're not doing machine learning and you're more interested in analytics, like Spark is cool, and you can think of it as answering questions in minutes instead of days. Some conditions apply, the rest of the time you receive an out-of-memory exception. But the out-of-memory exception comes faster, and so that's what counts. And this will be focused mostly on classic machine learning, and then is there anyone in the room who's really excited about deep learning? Wow, okay, that is a lot of people. So I will also talk about how these same systems can be used for deep learning. I guess a lot of people are trying to raise money in Silicon Valley, and I respect that. Does anyone who's really excited about deep learning have like a happy use case for deep learning they want to share? It's totally fine if you don't. There's no pressure. Okay, moving right along. Okay, so what's out of scope for today? We're not going to talk about how to implement your own machine learning algorithm. We're going to talk about how to use the ones in Spark. And if you ask me how these work, I'll just say gradient descent and disappear into the background, but I won't stray too far away from the microphone. And I know you have a lot of questions about debugging, and we can chat offline. If anyone wants to really talk about debugging, you can come find me after the presentation and bring your print off of a stack trace. And we'll go through it together. And if it touches a line of code I wrote, I will apologize. It won't make your code work, but it'll make you feel better. Okay. So maybe there's a bunch of reasons why you might want to do this. Maybe you're building recommendation systems. Maybe you have a search system with a bunch of hand-tuned weights, and the performance is not a lot of fun. Maybe you just want a new job, and machine learning sounds a lot more cool than like manually selected parameters. The other one is maybe this one tends to hit more a little bit in San Francisco. Maybe you run some type of social media site. Your budget for dealing with abuse is about one intern, and it turns out that that intern quit. So you've decided to replace them with a machine learning system. And that goes really well all of the time. But then you hire a second intern to provide you with more labeled data afterwards. And then they can be a machine learning intern, and then they feel better about themselves and don't quit right away. Not a guarantee. So how did I get tricked into this world of stack traces and sadness? So back when I graduated and I really didn't know what to do in the world, a small bookseller in Seattle came up to me and asked me if I wanted to build search systems. And I was like, that sounds really cool. Search is neat. And that began a long time of sadness. Then I went to another company because I was like, wow, this is really sad. I bet I'll go to a startup. And I went to the startup and they were like, hey, you've got experience building search systems. And I was like, yeah? How would you like to maintain our search system? And I was like, oh, well, I like money. And that went well. We had a search system and it performed not terribly. But our method of improving it was more or less going and being like, how important do we think it is that the user has visited this place in the past week? Let's try changing that number from a 6 to a 7. And then we would do A/B testing, also known as, I wonder if all of our users are going to leave. Let's try it on 5% first. And that was not great. That was not a very principled approach to building a search system. And so we hired some smart people from Google, because that always solves your problems. And as someone who's currently works at Google, and in the future will not, I encourage you to continue hiring people from Google. And the smart people from Google came, and they said, you know what the solution to this is we're going to do machine learning on your data. And I was like, that sounds cool. I failed that class in university, but let's do that. And then we built a machine learning model, and it performed worse than our hand-tuned weights. And we drank. We did it a few more times, and it actually went up to another local maximum, and it was happy, and then I quit and found another job. I decided that I should go to Google, and that was a good idea. And then I left again, whatever. Not overly important, but the long and the short of it is, I came into machine learning trying to solve a problem, and it didn't really, but that's still what I work on to this day. And now it can solve your problems, maybe. Hopefully better than it solved mine. Okay, so we're going to use a bunch of tools. I'm actually not going to do the demo, so we're going to skip Emacs and Vim today. But we're going to talk about Apache Spark. We're going to talk about Spark Testing Base. Do any of the Spark users use Spark Testing Base? Yay! Oh, one person. Oh, two. Okay. Please tell me the rest of you have test cases. Yes? Yes? Okay, cool. So if you don't use Spark Testing Base, that's fine. Just for the love of God, test your code. Spark Validator, we'll talk about it briefly. We'll look at CSV files, because like, yeah, whatever. At least it's not XML. And then we'll use XML. Okay. And the sample code is mostly in Scala. If it doesn't make sense, stop me, and we'll go into it. So for the people who are like totally not familiar with Spark, it's a general purpose distributed system. Yay! If you like took that like intro to CS class where they teach you like functional programming, and they're like, isn't this amazing? The computer could totally parallelize all of these operations because like you're not depending on any state. And then you're like, does it? And then the prof is like, well, no. Spark is kind of that system with stack traces on the JVM. But it's cool. It's an Apache project, and that's really useful because it means that if one company that's working on it like goes away, you don't have to worry. It's open source, and there's a governance model. It's faster than Hadoop MapReduce, and I'd like to give a shout out to the Hadoop MapReduce developers for setting the bar so very low. Thank you. Like MapReduce is an incredible system. It's great, but performance-wise, they made a lot of really excellent decisions around correctness and safety. And they were just like, well, performance, that's fine. There's no competitors. And that was true for a while, and now there's competitors. And there's two core abstractions, RDDs and datasets. We will look at a little bit of RDDs, but we'll mostly look at datasets. And so RDD stands for Resilient Distributed Dataset. And to be clear, datasets are built on top of RDDs, and they rather than the other way around. So I don't know who let people name that shit, but it wasn't me. But that's cool. Okay, so when we say distributed, what I actually mean is we have thousands and thousands of garden gnomes sitting inside of a data center. And when you ask it to do something, we ask all of these garden gnomes to do some work. And Spark is responsible for coordinating and collating the responses from all of these garden gnomes. Sometimes, because of how your data is laid out, Spark asks one of the garden gnomes to do all of the work. Then that garden gnome gets very sad and drinks. And then you get an out of memory exception. And you're sad as well. And then you can drink. There's beer. Okay, no, so it's not perfect, but we can think of it as Spark coordinating lots and lots of different workers. And the workers are JVM processes rather than garden gnomes, but functionally equivalent. So why do people come to Spark? MapReduce jobs can take longer than it can take to learn Spark. This is amazing. And the best way to learn Spark is with my books. Actually, the best way is with some free videos on YouTube, but that should not stop you from buying my books. And the other one is, if they're working in pandas or R or something, my data set or data frame no longer fits in memory. On my MacBook Pro, I bet the solution to this is distributed computing. And that's a solution which makes me money, and so it's a great solution. It might not always be the best solution, but it is an excellent way to learn a new tool, whether or not you need it. You can also just rent bigger and bigger computers, but then eventually at some point you find yourself needing to buy a mainframe, and no one wants to go there. I don't work at IBM anymore. I used to. Good people. Buy a mainframe. Okay, and the other part is some people come because they want that promise of this magically parallelized functional programming system that they like thought about in their like CS100 class when they were shown the light of functional programming. They're normally disappointed, but that's all right because there's not a lot of alternatives yet. And at that point, I'll have to find a new job. But okay, so we're going to focus on Spark ML today. But I think it's useful to note that Spark is not just a machine learning system. Spark is pretty much a grab bag of everything that they thought you might want to do with distributed computers. And in fact, it's a grab bag of everything we thought you might want to do with distributed computers twice. So we have two machine learning systems. We have two streaming APIs, which actually represent 3 distinct streaming compute engines. And well, we only have one. We have Bagel and GraphX, which are kind of like 2 separate systems. And then we also have GraphFrames, which isn't integrated. The reason why we only have one of these is that it doesn't work. So we didn't want to provide a second one, which was going to have the danger of working. So this one isn't integrated yet. It sort of works. If you want to do graph computation on Spark, I ask you to lower your expectations. For now, doing graph work inside of Spark involves poking around inside of Spark. And that's not normally what you want to do when you're building a system. You want to answer questions, not develop open source software.
Why is there 2 versions of everything?
That's a great question. One of them is papers. Spark comes from a very academic background, and new things are cool. Old things that are slightly improved is less cool. That one's sad. The other one is that this one you can think of as sort of providing, there's this RDD API which gives us very sort of low-level tools to build on top of. And so Spark built a lot of tools on top of this low-level API, but then it also introduced this higher-level API for datasets, and then decided to try and rebuild its sort of base tools on top of the higher-level API, because then it's a little nicer. But sorry, there are some restrictions around the data types that can live in this high-level sort of type, and so you don't want to get rid of the old things because then people get mad that they have to rewrite all their code, and that's why there's 2 versions of everything. How do I put this politely? Most of this could be described as maintenance. And so if you write new software, you should probably consider writing it on top of the dataset API as much as you can. The RDD API will never go away because the dataset API is built on top of it. But for example, you probably don't want to use Spark's first machine learning algorithm library, MLlib, because the only things that are going into MLlib right now are bug fixes, whereas like new features go into Spark ML. And the same thing is true for streaming. All of the new streaming stuff goes into structured streaming, and the old dstream API is not really being updated.
Isn't it about efficiency as well? Because when you abstract, like when you structure your data.
Right. So the data at this level has to be essentially all of the things that are Java serializable with a few minor restrictions can be worked with on the RDD API. However, the dataset API places some additional restrictions, and these are additional restrictions that let us do really nice things, like we can do direct operations on serialized data during sort steps and stuff like that, and that's really useful from a performance point of view. And so there's some performance benefits to writing on top of this as well. What? I think so. Is that a good answer? Okay, yeah.
The 2 streaming APIs you mentioned,
yeah.
Are they, just in short, are they for real time or real time data source?
Define real time.
For example, you get data from social media sources in real time while people are posting
Sure.
this.
What type of latency do you consider real time?
That's very good question.
Yes. So if your definition of real time is measured in like, let's say, for example, you were going to try and do high frequency trading. Spark would not be a real time streaming system for you. At that point, you go and you hire some very smart people and you write everything in-house and you never share it with anyone. On the other hand, if what you want to do is maybe classify tweets to escalate them to customer service and do like responses, totally, we're fine. Like no one will notice the additional like however many milliseconds latency that I'm not going to quote specific numbers because then I can be proven wrong.
MBs or
Well, oh, no.
MBs?
No, seconds, and milliseconds, maybe hundreds of milliseconds, but this is recording, so I don't want to say anything below that.
So get just a final question. So while they are real time, you get consistent data. Very hard.
Okay, so there are, if you're training streaming machine learning algorithms, for example, streaming machine learning algorithms will not result in the same results as if you trained on the batch data because of how we implement them. It's not great, but it is what it is. Like if you mean, does it produce incorrect results? It produces correct results with the data it's seen so far, but if it's missing a chunk of data for a time period, your life gets really complicated, and there is a book written by a friend of mine that is not yet published that you should buy as soon as it's published. It's like Streaming with Spark or something. It's an O'Reilly Spark streaming book, and it goes into all of the pain involved in making that shit work. And it is a lot of pain.
So the graph X and Bagel, so isn't it Prego?
Prego exists too. This is special.
There's another library called Bagel.
Yeah, I mean, imagine looking at an API and saying, you know what I could do better is rewrite it. Yeah. And that worked about as well as we thought, but only with hindsight. Looking forward, it was a great idea. This is awkward. I know these people, and they're nice people, right? Like these are classic engineering mistakes which we make, right? Where it's like, I know this system. Oh, this part looks weird. I'll just make a new version of it. Then it turns out there was maybe a reason it looked kind of weird.
And now you have 2 weird APIs.
Yay! And then we add a third to keep it entertaining.
Yeah, is the order like, is it your order, Scala, Java, Python,
Oh,
or performance?
that is an excellent question. Realistically, Scala for now, gives you the best performance with Spark. Java is pretty much the same. There's some slight unboxing costs with native types, but you probably won't notice that unless you're doing something like high-frequency trading. Python has gotten a lot better recently, like within the past 6 months. But the thing about things that get a lot better recently is it's normally at the price of a few extra stack traces until we sort of settle on the new things. And so there's some new APIs we introduced to make Python a lot faster. And if you want to work in Python, please use them and tell us what we fucked up, and we'll fix it. But if you're not the kind of person who's like, you know what I love to do is try out new APIs on my weekend, it's not going to be super fast. Okay. We good? Okay, rocket. Okay, so as a licensing requirement, as a big data instructor, and this isn't really a class, but I do want to make sure that I don't cross any union rules. I am required to put a word count example in every one of my presentations. And this is, I imagine the MapReduce people don't really like it because it takes 5 slides. But Spark was definitely well optimized for the case of word count, which is actually somewhat representative of big data tasks in one small way. And so this uses the old RDD API. SC represents our Spark context. Text file just says I want to load in some text. SRC can point at something inside of HDFS, Google Cloud Storage, that's the one from my employer, and therefore the best. S3, or like really any distributed file system. It could even point to NFS for those of you who missed the 90s. And then we've got this flat map function, and it runs on our input. And then the nice thing about this is that this does not modify lines, right? This returns a new distributed collection, which is tokenized by space. And because I live in North America, I can pretend that's a reasonable tokenization method. It's great. The only problem is my first job, they asked me to port my software to Japan. Then I quit, it was good. And then we go ahead and we can key all of the words with the number 1. And then we can ask Spark to take all of the values with the same key and combine them with some provided lambda function. And then we save the result out. And this is relatively basic as far as things go, but one of the nice things is nothing happens until we call this save as text file here. Spark builds up a graph, and this graph is all of the things we've asked it to do. And then when we call save, Spark evaluates the graph and actually does the work. And this is called lazy evaluation. That's really nice. It comes with the slight problem that you can call save here, you'll get your stack trace here, and the actual error message will be that your input file does not exist. And this can result in some confusion when you're debugging, because it can look like everything is fine until a different point in your code, and a whole bunch of other problems as well. But there's some really cool things that we get for this cost. One of these things is if you're a MapReduce developer, you might be going, why did you put this in 2 separate steps? You could put this in one single pass over your data. And that's true, but the nice thing is Spark will actually combine these 2 steps for me into an iterator-to-iterator transformation within a single pass over my data. And so the nice thing is I don't have to think quite as much as I did when I was writing MapReduce code. That's really all I have to say about the word count example. It's required, but hopefully y'all don't mind too much. Okay, if anyone's really excited about today, and you don't have to be, the pictures are already taken, there's a Python notebook and Scala notebook, which you can go and play around with, which trains the machine learning pipeline that I'm going to look at today. And if you want to use it, you'll need access to Apache Spark. You can install it on your local machine, or pretty much every cloud provider has a notebook environment. Yeah.
Are you going to post these slides later?
Yeah, I will tweet these slides as soon as the presentation is done, unless people ask me questions, in which case it will be presentation plus J minutes, where J is the length of questions, / time to get a beer. Assuming there's still beer left, I don't know. But yeah, don't worry, I'll post these slides. You don't have to take pictures of them. You can, though, make me feel like a superstar. Whatever. No pressure. Okay, so we've talked a little bit about Spark datasets and RDDs, and we've looked at word count, but for machine learning, we don't really write our Lambda functions like that super often. What we actually do is we use things called transformers and estimators, and we use them to build up pipelines. Is there anyone here who comes from a scikit-learn background? Yay! Does this sound at all familiar? Yay! Okay, so for 3 people, this is going to be really easy. And so the rest of you, it's not going to be so bad. Because the scikit-learn pipeline API is actually really amazing, and it makes it really easy to think about these problems. So transformers, we can think about them as things which don't need to be fit. They don't need to see any data. They can be immediately applied to new records. Estimators are things which have to be trained on a data frame. So a classic estimator would be linear regression, but other things that are estimators that we might not think of as estimators are things like a string indexer, which wants to see all of the strings to index them to unique values. Although there is hashing TF, which does a hashing transformation. It doesn't guarantee uniqueness, but gives us a similar performance as a transformer. And pipelines are a really nice way to put together all of our estimators and transformers in a way where we can fit the entire pipeline at once, and we can also save some of the time the entire pipeline at once. And some of the time saving the pipeline will just result in a stack trace, which is more or less Spark tradition. But let's start with loading some data. So as a rule of thumb, if your data fits on a floppy disk, it is not big data. Sorry, salesperson. I've been in sales meetings where we've sold those people big data systems. And I like money, but you probably don't need it if it's going to fit on a floppy disk. It's okay if it fits on a floppy disk. Spark will still work. However, if you have less than about 200 records, Spark will not really work all that well. So please make sure that you have at least 200 records. And there's nothing wrong with building a system that starts small and is going to grow big. But like if you build a system with like 1 test record, you'll get really wonky numbers that don't make sense. And so just keep in mind, Spark made some assumptions as a big data tool that it was going to have big data. And yeah, it's totally reasonable to downsample your big data to small data while you're developing your initial pipeline, and then train it on actual big data once you've got an idea of what it is you want to build. Spark SQL is how we're going to load our data. And if this name sounds happy to you, how many people here like SQL? Yay! The exciting news is you can put SQL in this. For those of you who don't like SQL, the exciting news is you can take SQL from other people and not have to understand it and run it. And that's fun, because the amount of time that I have spent rewriting someone else's SQL statement into Scala code and then getting it wrong is long enough that I probably should have read the SQL 92 spec. But okay, so we can specify a whole bunch of parameters. I'm going to use some sample data from MNIST because everyone loves the hello world of machine learning, or at least I think it's MNIST. No, I changed the demo, and I don't remember what I changed it to. So we're going to find out together. But we can specify properties. CSV is simple. Spark supports a lot of things, Parquet and all of that stuff. Is there, as a quick side note, anyone here who uses JSON data? I am so sorry, but I have good news for you. Okay, so for those of you who use JSON data, do you completely know the schema of your data? Okay, that is 0 people. Oh, okay, half.
A little bit.
Okay,
Most
so we've
of the
got,
time.
I see. Okay, so like a quarter. So 1/4 out of like 8 people know what the schema of their JSON is. And so that's pretty solid. And the nice thing about this is here it's being done on CSV data, so it's not very impressive, because we can just look at the header and then the row below it and be like, yeah, we good. But with JSON data, that's not going to cut it. And the nice thing is you can do this on JSON data, and Spark will infer the schema for you, and then you can ask Spark what the hell it is you're doing. And Spark will be right pretty often. And if it's wrong, it has this option that says, don't use sampling, just look at every record and tell me for sure exactly what my schema is. And we'll do that, and then you will be sad because you will realize you have a billion fields. But that's okay. And so this is just loading some data. And I didn't specify HDFS or GCS or anything here. So it just uses my default file system, which when I'm running it is pointed to GCS. And we're gonna train a decision tree. Yay! So much excitement. So we've done step 1, data loading. Super fast. The nice thing here is, since we didn't for schema, Spark will actually check that the file existed for us, because it has to do that to do schema inference. And so that's cool. If we were using the RDD API, we would not know if our data existed yet. So when step 1 was done, step 1 would be more like, we've asked someone to do it eventually, but it's not done. Okay, and now we're going to do data prep. And we're going to do that in one slide, which is completely unrealistic, because this is probably where you're going to spend most of your life. But the cool thing is, I'm going to show you like the very minimal data prep tools in Spark. There are a whole host of other data prep tools in Spark, and I have a link to the documentation that gives you that list. And so what we do is we take the 2 things which already happen to be numeric, which is age and a numeric representation of someone's education. I have no idea what that is, but it's American, so I'm sure it's great. And we put them together into a vector. And vectors mean math. And so now we're ready to do machine learning. But then it turns out we also need labels. And that's because we're training a decision tree. We're not training, someone who doesn't need labels. So we're going to have to take our category, which is inconveniently not provided as doubles, and we're going to turn it into doubles for us. And we'll use the string indexer so that we're guaranteed to actually have distinct numbers for each label. And then we'll make a pipeline of our assembler and our indexer, and we'll run it on some data. So in this case, this vector assembler doesn't need to be trained on any data, but our string indexer does need to be trained on some data. And so we can put them both in this pipeline, and we can train that pipeline, and it will train the parts that need to be trained, and the parts that don't have to be trained will just be copied over. And it'll give us this pipeline.fix, gives us back a model, which represents everything in that pipeline fitted. And then we can use this model on future data to predict results. So this is our very fancy pipeline. We take data, we turn it into other data, and then we turn it into other data. And the other data is actually at a stage we could give it to a decision tree. Okay. Ooh, okay, and I decided to switch from Scala Python in the middle to keep it fresh. Also known as I pulled these slides from 2 different decks. But that's okay. So we train a decision tree classifier, and we tell it this is our label column, and these are our features, and then we fit it. Or we would actually normally make our pipeline, and we would put all of these things together. So we could just fit it on the prepared data, but we could also just put it together in this pipeline and fit the entire thing in one go. It's a little simpler. It's nice. Oh, the other thing which I should have pointed out. So here we're setting our input column and our output column, and that's like, that makes sense. We would set where our data was coming from and where we're writing it to, but there's a lot of other things that we can set. And so if you were training a decision tree or a random forest, you might set like a maximum tree depth or other things like this. And your specific algorithms are going to have a whole bunch of different parameters on them. And because we got the API from Python and implemented it in a strongly typed language, we threw away all the types. So if we gave this data, if this data frame or data set was not the right kind of data, we would not know until runtime, which is the best time for our exceptions, right? Compile time errors are they just take the fun out of development, right? It's like far too easy to know what's going on at that point. Ooh, question.
Yeah, question about the input and output. Input is the input data for training purpose, and then output is the result from inference.
Yeah, although, so for example, here, right, our input is going to be the age and education number, and our output is called features.
So you use 2 colors to get the result of the feature.
Yeah, we can use multiple columns of input for a single stage. Because some things, we wouldn't want vectors to only be able to consist of one thing. We want vectors to be able to consist of many different things. And so we're able to say our input is this list of columns. And this is useful. And so yeah, we use this feature step, and we use the vector assembler both at training time and at inference time. Because at inference time, people aren't going to hand us fully assembled vectors. They're going to come to us with the user's age and education number, and then we're going to put it together into a vector and hand it down to the next step for inference.
I think why I'm confused is because I came from the world of TensorFlow, and then is there mining with input output with some terms in TensorFlow?
Probably. I don't remember though. Does anyone else here use TensorFlow? Okay, we got like a meh answer. So the answer is yes, there totally is, but I don't know them, and so. Yeah.
Last year I went to another meetup. To my understanding, that's to parallel, which is from Spark, and the community added the machine learning library to the Spark, but it's grow. And the other side is TensorFlow. It's grow in parallel. So this is 2 streams. I don't know for now, they trying to merge together or they still grow in parallel. So this is maybe the question I will be myself.
Is TensorFlow distributed or is Spark? Is it distributed?
So there is a TensorFlow distributed compute system. I can train on multiple TensorFlow nodes at the same time. I do talk about TensorFlow on Spark near the end, so maybe that slide will answer your questions, although I think the odds of that are low. But you can hold out hope for the very end, at which point it will be too late. Okay. Yeah, I think it's easier to just think about these things as like inputs to a function rather than being overly concerned about machine learning right now, right? We could just think about chaining these functions together, and all of these things work on a data frame. And so vector assembler, when we call transform on vector assembler, we give it a data frame, and it gives us back a data frame, and the vector assembler will pull the age column and education number column from the data frame, read those values, and use those values to create a new column called features. And it'll give us back a data frame which still has the age and education number in it, but also has this new column called features.
So in this context, the data frame is kind of like a record.
So yeah, when I'm saying data frame, I just mean like a distributed collection of records. But yeah, we can think about it on a per record basis as well. For the vector assembler, it's operated on a per record basis, but on the string indexer, for example, the data frame isn't just on a per record basis, right? We actually have to do a sort step to figure out like what all of the different unique strings are and how often they occur. Well, by we have to, I mean Spark. You don't have to do jack shit. Just ask Spark to do it. Does that make sense?
So what's the function to combine these two columns together and generate the output column?
I mean, that's the vector assembler function.
No, I think we're missing like when we jump to the Python slide.
Ooh,
the transition is kind of shady.
Gotcha. So this pipeline thing is a pipeline which gives us an assembler and an indexer as one unit, and then we can call pipeline.fit, and it'll take a look at all of our data, and it will transform it with the vector assembler, and then take the result of transforming it and fit the indexer on the transformed data. So it'll run the assembler and then the indexer. And then if we wanted to, we could take that resulting model that we get back from calling fit, and we could take that model and we could transform the data to look at it. Or what we would normally do is we would, shouldn't have added animation to that slide. We would normally make a pipeline which has those two stages and the new decision tree classifier stage. And then what would happen is the pipeline consists of an assembler, an indexer, and a decision tree. It transforms the data with the assembler. It fits the indexer and then transforms the data with the fitted indexer. And then it takes that transformed data and feeds it to the decision tree to fit the decision tree. And then it will actually run the same predictions. It'll run the decision tree predictions on its input as well. Did that transition make sense? I'm getting to like 0.5. Okay.
General question. In terms of the whole work, right? You were collecting data, cleaning data,
Yeah.
and then predicting, right? So in your experience, what is the percentage of work that's needed? Like, so is it the engineering part or the machine learning part?
So the slide, which is this part, the data prep cleaning, this part normally takes like several pages and a lot of sadness. Because like here, the data is already pre-cleaned for us, right? Like a lot of the sample data that you get from machine learning is stuff that people have already gone through. They've removed the outliers. They've encoded the data in a way that's like easy to work with. So you don't have to do a lot of stuff here. But if you're getting raw data from like sensors or humans, it's garbage. People are terrible. Yeah, your job is mostly figuring out what parts of the data are not garbage, and then figuring out good representations for the parts of the data which remain. So you'll spend all of your time in the part that we're going to skim over. But this part doesn't sound cool, right? Data cleaning specialist? Fuck no, I'm putting machine learning specialist on my resume. Although, I mean, if you talk to someone and you're like, I'm a data cleaning specialist, they might be like, how much money do you want? But I mean, depends what you want to do with it, right?
How about automating that work, also cleaning the data?
There are many people who are willing to sell you a solution that claims to do that. Some of them might. Maybe. It's hard though, because a lot of this often depends on the domain knowledge of what we're working in, right? Like, if I'm getting data back from humans, right? If I'm getting like survey data, the stuff that I'm going to do to clean it, to like kick out the person who is like, sex is yes please, you know, is different than if I'm getting data from IoT sensors, which are like, it is 700 degrees, it is -5 degrees, and I'm like, right? And I'm going to have different things depending on which domain I'm working in. And so often anyone who offers to sell you like a packaged solution here, what they're really selling you is a consulting contract wrapped inside of a packaged solution so that it looks better to both of your respective companies from an accounting perspective. This is based on my 1 semester of business class that I got like a solid 65 in, so like, don't trust me on this part.
So how you included the loop, for example, the training and validation, training time, and again?
Oh yeah, right. So that's a really good thing. So how do we do the train test validation loop? So it's pretty common that people will put this in a notebook, and then they can go back and they can edit their notebook, right? So they can have their, you know, cleaning, they can do their training, they can look at the model and be like, wow, that's garbage. And then they can go back and they can start inspecting the individual stages that have been fit to see what's happening, right? So this pipeline object has a transform method, but I can also go inside of the pipeline object and ask it to tell me about any of the stages that I fit. And then I can be like, that's interesting. I have like 10,000 entries for the postal code. I spent too long in America. Null. Oh, maybe I need to do something about missing data, right? And then you go back, you fix your missing data problem, you fit your pipeline again, go grab coffee, or, you know.
That's a manual process. I just wonder how the automatic define how many loops and until certain criteria to reach it and stuff.
Oh, well, so I mean, so if you want to like define the number of iterations of your machine learning algorithm, that's totally doable. And so in that case, it's not about doing data cleaning loop, it's about doing the loop of your gradient descent. And so despite that being a feature on almost every algorithm, each algorithm decided that it wanted to have its own parameter for number of iterations and convergence. So there is no one answer, but the actual answer is like, you know which algorithm you're fitting, you go and you look at the Java doc or PyDoc, and you scroll down and there will be like num iterations or like number of iterations or number _ iterations. You'll find the one that matches that, and then you'll also look if there's like a, you know, convergence test or something else that you can set, and then you'll set that parameter as you want, and then you can do that either by just adding it here as one of the parameters where you're constructing it, or you could do it with dt.set like num steps, like 7,000 or num iterations.
Just to correlate with scikit-learn, is there an update kind of method to have training with new data without using them?
So the question is there an update method where we can do training on new data without essentially redoing all of our work? That would have been a really good method. So the answer is no. Well, the answer is sort of. If you use the old APIs, which I told you not to use, you can get at an internal method to do updates if you lie about being inside of package org Apache Spark. This is a terrible idea, but I know several people who do it. And so it is possible. It's a thing not to do, though, because your code will just stop working. Well, best case scenario, your code will stop working. Worst case scenario, your code will start to produce incorrect results at some point in the future when we change the meaning of that method, because it's not public, and we didn't make any guarantees about it. The other one, though, is it's a little better. Is for some of them, you can, if you trained your model previously, you can use them as sort of the initial weights. So you're not always starting from the same like training state, but you do have to feed it all of the data. But you can use the initial weights from a previous run to bootstrap your training to go a little faster.
So you can checkpoint, for example, you can checkpoint those parameters in the model?
Yes. unfortunately, it checkpoints them in a Parquet file. So it's not exactly human readable, but the machine can read it. It's not, we didn't pick the best data formats for this. We picked the data formats that were already integrated into Spark, which was Parquet and JSON. Whatever, engineers.
I think I understand the first part of vector.
Yay!
Vector assembler, which is one of at least a lot of functions, but the other part is indexer. Right? What the indexer used for?
So what is a string indexer used for? That's a great question. And so the string indexer is used for when I have categorical data as strings. Or actually, I can even use it on other categorical data despite its name. It supports many different types of things that look vaguely like a string when drunk. And what it does is it takes our categorical data and it encodes it to distinct doubles. And this allows us to use machine learning algorithms which in Spark assumed that all of their categories were going to be numeric. And so this category indexer, that's where it's commonly used. And it can be used on like training features, or it could be used, like for example, if we had like users who went to college, users who went to high school, we might have like different strings and we might encode those into numbers so that Spark could have happy fun times with it.
I see in the Terraform world, that's the name hot, something hot dot.
Oh, one hot encoding.
Oh, one hot.
Yeah, slightly different, but similar. Yeah, but yeah, that's pretty much close enough for all intents and purposes, except for the slight part where this behaves differently. But that's okay. And the other important thing about this is the indexer also has an inverse method. So if we use it for encoding our labels, right, when we do our predictions, the values that we're going to get out are going to be doubles, and the values that we actually want to get out are like the strings that were our labels. And so we can take this indexer and we can essentially tell it to run itself backwards on the results so that we can actually get human understandable labels out.
Okay, so now you have 1, 2, 3, 3 columns
Oh.
train on, and then you get the result
Yeah.
For the feature column.
Yeah.
Oh, not feature, but also category index, and then you have you will generate maybe another result for additional column.
Yeah. So in this case, sorry if I keep going back and forth. In this case, these are our only features. If I wanted more features, I would put them in this list, and it would get combined together into that vector. And then, where did I animate that? And then here, there's actually an output column on decision tree classifier. It's just not specified because it's just outputting to the default feature column. Sorry, the default prediction column. And so this, says this is where I'm reading from, and you could imagine a default parameter here that said like output column is prediction. And then when we run this, we can look at the predictions from the decision tree. Okay, it is what it is. Yeah, and so this shows running the same data, running the pipeline on the same data, but you probably don't want to just train a machine learning model to predict the results that you already know the labels of. I mean, that's fun and important, but the main thing here is that we can run this on new data and we'll get our new predictions. And for the person that was interested in streaming, you can run this part inside of streaming and your life will be happy, and you can find out if your users are trying to steal your money or whatever it is you're worried about. Oh yeah, and here's our prediction function, right? Yay! So we select our prediction. Okay.
Previous slide actually got 2 models.
Oh yeah, that was just 2 different ways of training it. I probably should have only put the 1. Sorry. Just pretend that this slide, this was never here. Okay? Okay. Sorry. Cool. Yay! Okay. And then we have our predictions. We can also go and poke at our decision tree, and we can ask our decision tree like, hey, what's up? Who are you? And that's fun. And it, yeah, cool. It's a lot of features. maybe it's good, but given its inputs, there's perhaps a chance that it might have overfit just a touch. You know, the difference between someone who's 12.5 years and you know, whatever the other one is, it's probably not that big. So that might have been an interesting slip point to pick. And we can predict the results on new data, and that's okay. It might be overfit, it might not. Let's just serve it, right? We trained a machine learning model. Let's serve predictions. There's no need to figure out how good our model is. That could take literally minutes. And so we have this evaluate function, and it takes in distributed data frames. And this is nice, provided that you're willing to do your training with either Spark streaming or Spark batch. However, when I talk to people, their excitement about deploying a big data system into the hot pipeline, into the hot path for their website, resembles that of my excitement about trying to get a green card in America. It's not really all that high right now. And so embedding Spark just to serve our models is not so good. Also, if you're the green card interview people, that was a joke. I'm very excited. Please give me a green card. Okay. Yeah, probably should have thought that one through, right? I'm used to not thinking. This is why I work in open source. Okay, so what do people do? There's a bunch of things. If you happen to work at a company which has existed for a while, maybe you work at the government or in Ottawa, there's a good chance that someone back in the 90s either wrote a pile of C++ code or C code, or hired someone to write a pile of C++ code to do model serving. And then if you're lucky, your model, when you turn it sideways and kind of squint, can be made to look kind of like that model they trained one time. And then you can write a bunch of code to manually serve it. The other one is, some people just say, you know what, I have a problem, and I'm going to solve this by copying and pasting. That works. But now you get to maintain a giant pile of copy and paste code. Yay! So what people do is they copy and paste the serving logic outside of Spark and build it separately so they don't have to include all of Spark. And that's maybe not a great choice. The other choice is to find some other people who ran into the same problem and go, hey, how about we work together on some open source? And then they go, sure. And now you and someone else have the same problem. Oh, yeah.
Does Spark work well on, say, like AWS Lambda or some kind of like serverless?
Define well.
What was the question again?
Oh, so the question is, does Spark work well on AWS Lambda or serverless platforms in general? And the answer is, I mean, provided that the serverless platform supports Java, yes, you can put Spark there. Spark is not small. And so putting Spark there is a choice. And as a cloud provider who makes money when you use more resources, it is an excellent choice. As someone who is perhaps giving me money, perhaps not an excellent choice. But I do not want to talk you out of giving me your money. So we'll leave it at that.
Are those our only options?
No, there's another slide, or at least there should be. Yay! Okay, no, I find that like setting the bar really, really low does a really good job, so that when I'm like, hey, you like XML, right? People are like, well, if the alternative is a 300 meg jar, yeah, I like XML. And that's the alternative. Yay, okay. And so Spark has PMML support, which is a standard from people who like XML. And there is nothing wrong with being a person who likes XML. It is supported in the old APIs that I told you not to use today. And in the new APIs, it doesn't work today. But if you're willing to build your code from master, it does work. Or if you're willing to wait a few months, I wrote the code to add PMML support to Spark 2.4, and you can save some of your models to PMML. Oh, thank you. It was like not that much work. There was a live stream of it. If anyone is like looking for something to be calming and listen to a lot of swear words as they're falling asleep. And me going, God, fucking, sorry. I don't know where you post these. If it's Apple, then I'll stop swearing.
What is a PMML?
Excellent question. So PMML is Predictive Model Markup Language. And I'm pretty sure I remember that acronym correctly. And it's a bunch of people got together, and essentially they had this problem, but way before Spark, like way back before scikit-learn these things, and they were like, wow, we have all of these different things to train models, and all of these different things to serve models, but no one could agree on a format. What about if we made a standard? And then because it was like, I think the 90s, they were like, standards are XML. And that's how we got PMML. There's a new standard because someone looked at that standard and then all of the competing other standards and decided the solution was another standard. That XKCD comic is pretty on point when it comes to model serving. And that standard is called PFA, which is a reimagining of PMML by people who like JSON. I'm sure there are other differences between PMML and PFA besides XML and JSON, but I just don't care. So I don't really care, because nicely enough, the people who support PFA also tend to support PMML, so it's fine. Just so long as everyone supports every standard, my life is okay. And there's oh, I should probably be plugging the standard my employer is part of, but it doesn't work with Spark yet. So yeah, oh well, whatever. Don't worry, we'll fix that later. Okay. Oh, this part is one of the parts that my employer likes. And so one of the things that's kind of rough is that you can go through training your machine learning model, but then figuring out how to serve it is kind of like an exercise in going and looking at random projects on GitHub and being like, are you my father? And then often they're like, no. But they say that like 3 weeks later when you're like, you don't compile, do you? And that's after you track down all the Fortran libraries it depends on. And so, and there are some that work. I should perhaps sometimes pro into some amount of exaggeration and fun. But Kubeflow is the idea that what we can do is we can write things that run on top of Kubernetes. And Kubernetes is very cool, and so that'll totally get us money. And we can write training stages which are sort of matched to serving stages. And so there's a TensorFlow training stage which maps to a TensorFlow serving stage. There's Selden Core which can serve a whole bunch of things. And the idea is that we can put them all together into one project so that you don't have to like go and figure this all out on your own. It doesn't work with Spark, but it's on my to-do list, and I got like at least 25% of the way through of maybe starting. And it'll probably happen, honestly, sometime this year. This Kubeflow will support Spark. But since this is being recorded, this is not a guarantee, and is definitely not like a product delivery time from Google or anything. This is some code that I write in between airplane flights. Kubeflow is written by like fancy people, but the Spark integration is written by me when I'm like bored. Okay, right. So maybe you listened to this talk and you were like, wow, that was really sad. I don't want to train your decision tree. That's not cool. And there's a whole bunch of other things you can train as well. Yay! And so the main thing here is if you just type these into the Spark documentation or click on these links when I tweet the slides, we'll take you to there and you can see the list of all of the different algorithms that Spark has implemented for classification, regression, recommendation. And oh crap, there used to be a second slide, but it looks like I deleted it in the minute beforehand for future prep as well. Yeah.
Is there one for convolutional neural nets?
Not exactly. So the question is there one for convolutional neural nets? And there is sort of one-ish that a coworker worked on, but you probably actually want to use a different project, which I'll mention in a moment. I promise, I'll get back to you. Okay, yeah. There's other ways to serve besides standalone microservices. It's not super important. Yeah, by the way, before you start serving your model, you should check to see if it works. He is good. saving a test set is effort. You can use Spark as a built-in cross-validation tool to automatically, oh, I'm pressing the button in the wrong direction, that's why. Okay, and you can use cross-validation to automatically fit some of the parameters, what was it? Some of the parameters you were talking about. Like, for example, what is this fitting? Oh yeah, the naive-based smoothing parameter. And then we can automatically fit our parameters on our model, or as I like to call it, a great way to overfit on my data while pretending I didn't. And so if you use cross-validation to do this fitting, please save the test set and don't just depend on this, because otherwise you can just overfit. But if you don't really know what you're doing, this is a not particularly principled approach to figuring out what your model, what your estimator parameters should be. Cross-validation, false sense of security, please still test if you're gonna do this. There are a whole bunch of problems that are domain specific. Search systems, rank bias for results that are displayed, non-displayed options to users could actually be what they were looking for, but we won't have any samples with those chosen. And then there's some papers on how to do this. You should go and click on those links if they're things that you care about. Yay, okay, TensorFlow on Spark. For the one person in the back room and someone in the front room. And so if you want to run TensorFlow on Spark and you just like writing TensorFlow code, but all of your data is in HDFS or S3 or somewhere, you can just take your data, put it into an RDD, and then run TensorFlow on top of Spark. And Spark will just essentially act as the feature preparation data providing layer to TensorFlow to do its fancy deep learning stuff. That doesn't sound like a good idea to you. There's an alternative called TF Transform that works on top of something called Apache Beam, which works really well if you're a Google Cloud customer. And if you are, thank you for giving us your money. And if you're not, it doesn't work so great yet. It's getting there, but if you try and use it, it'll go poorly. So yeah, this part, TF Transform, don't use this in production today, unless you're a Google Cloud customer. If you're a Google Cloud customer, definitely give us your money, and I promise it'll probably work. And there we can do our feature prep, and we can do it, this is just standard Python code, but the nice thing about this is that it will, here's another one. So we can see mean, scaling to 0, 1. This is the string encoding, but done in TensorFlow. And all of these things will get transformed into a TensorFlow model for serving time. And that's nice because if you do the Spark one, where you do some data prep in advance by hand, it doesn't get saved, and you get to write your feature prep logic by hand in a format that TensorFlow can understand. And that's a great way to waste several months of your time and then later break something by accident. And so if you do that, keep your resume up to date. Yeah, and so how this works is has these things to the TensorFlow graph, so mean, standard deviation, quantiles. We analyze some data with it, and we output constant tensors into the graph that TensorFlow can use, and it'll have happy fun times, and everything will work, probably. There's a bunch of things built into it. String to int is similar to the one we looked at, but it's two. And this is the catch, though. Right now, it depends on a software project which doesn't work outside of Google Cloud today. I mean, it sort of does, but specifically the Python part, which is what TensorFlow depends on, doesn't work outside of Google Cloud today on top of Beam. And so you have to wait for some things to get fixed. If you want to join us fixing these things, I have a Jira number, and it's an Apache project, and pull requests are welcome. And if no one reviews your pull request, you can email me, and I know where the developers live. Literally, I went to school with some of them. It's really convenient. I mostly work on Spark, but I know where the Beam people live, and so we can go and get that stuff fixed out. Here's a slide which shows you that everything is terrible, but in the future, these very stylish orange lines could become black lines that indicate that they work. But not yet. Okay. Ooh, yeah, and use containers because of the future. Question.
What does Beam do?
Oh, excellent. Okay, sorry, I skimmed over that. So Beam, you can think of Beam as being like a high-level language for allowing you to write code that is portable between systems like Spark and Flink and Dataflow. That is the promise of Beam. We have not yet delivered on all of that promise, one could perhaps say, but it's a very exciting promise. Right now it's a portability layer which works fine in Java, but if you want to use the portability layer in Python, it doesn't work. And that's why this part doesn't work yet. But it's going to, probably.
Don't entirely understand the TensorFlow and Spark stuff. Does each worker node have its own GPU? Or?
Yeah, let's go back here. So that's a great question. So TensorFlow on Spark more or less leaves it up to you to provision a cluster which is well suited to running TensorFlow. And what that means is if you want to use GPU acceleration, which you probably do, you should provision all of your nodes to have GPUs on them. And then it doesn't currently today do a great job of running in a mixed cluster environment. And this is just because of the state of the cluster managers today. Like Yarn doesn't do a great job of assigning GPU resources. And so it's just fundamentally difficult for Spark to explicitly acquire resources in a safe way. And so it's up to you to build a Spark cluster, more or less for running TensorFlow, that has GPUs on all of the workers and not schedule multiple jobs per worker.
So do people generally, when they say do like hyperparameter research, do they do like one run on one GPU, or do they kind of parallelize the whole gradient descent for one iteration through like say one block?
So it depends if you have big data or if you're just doing hyperparameter tuning on small data across a whole bunch of different nodes. If you're doing hyperparameter tuning across a whole bunch of different nodes, then you run many epochs on each GPU, and you're just like, yo, go have fun. Otherwise, there's a parameter that you can set more or less where it's like, hey, every so often this is my like interval, and we should all talk after this interval and be friends and distribute your data. And so that's like, it depends on if you have like big data or small data. And if you have small data, you probably don't want TensorFlow. Unless someone convinced you that you really do, which is have fun. Good luck. Cool. I'm getting like a cool-ish vibe. We can talk with like alcohol when the recording isn't on.
Does that mean if you use a GigaDL decided by Intel?
Oh yeah, okay. That's a great question. So the question is like, what about Big DL from Intel? Isn't that pretty amazing too? And the answer is, I work at Google. Okay, so Big DL is really interesting as well. But I think that the different vendors are approaching solving the same problem in different ways. And for now, there is no clear one true way yet. And that's exciting for us because it means everything we learn might become useless.
It's like TensorFlow has like 20 different APIs.
Yay! Yeah, and the comment was that's right, TensorFlow has 20 different APIs. And that's like, yeah, why pick one API when you could have 5? Or 20. I don't know. I wonder if anyone's done deep learning on deep learning APIs to generate deep learning APIs. Oh man, I just thought of a new talk title. No one. Oh, well, okay. If anyone wants to do that, like, come talk to me, and we'll put together a CFP together. I know it'll go terribly, but I'll have a lot of fun. Okay. Yeah. So I mean, Big DL is a thing. There are other. TensorFlow on Spark is. There are actually multiple ways to integrate TensorFlow inside of Spark. TensorFlow on Spark just happens to be the one that I can get to run reliably. For values of reliably, which means 1/3 of the time it still crashes. Okay, let's end on that happy note. Wait, no, I haven't tried to sell you my book yet. Okay, skip this. Okay, updating your model. We're like way over time though, I think, yeah?
Just 5 more.
Okay, cool. Testing is important. You should do it. Just because you're training machine learning models doesn't mean you don't need to test. Also validation. Oh yeah, cool. So 52% of people running a Spark job have not had a serious outage, which means, you know, their stuff still works, so they're probably running word count. 16.2% of people have had a serious outage, which I assume means they had to update their resume. And 30.9% have had an outage, which, while bad for the business, did not involve updating their resume. And so, as someone who lives somewhere between here and here, and if anyone wants to talk to me about my time at Amazon, I'm more than happy to, this is not a fun half of the graph to live on. You want to live over here. And so please test your code, because otherwise you'll be sad. And the nice thing is you also need to do validation, because I can test my code, but what about if my data sources change on me? How many people have had a data source change on them? That's like only 3 people. I assume that means we've reached the part of the talk where everyone is asleep. And that's all right. It's been a long day. But, or you're just very lucky and you work with good data. And in that case, that's amazing. But eventually, one day, you'll work with a wonderful coworker. And their name is going to be Schmer, because that name is not particularly assigned to anyone. And so Schmer one day will come in and they'll be like, well, we have these really nice tests, but I want to change some data. But when I change the data, well, when I change my schema, the tests fail. I don't want to get rid of this field and have to go update everything. So I'll just stop populating this field. And that'll be a great day. And then your machine learning model will come in and be like, I'm going to train. And it'll be like, wow, that feels weird. Oh well. And then it'll go into production. And that won't look like it. And it'll be very sad. Or they'll change the meaning of a field, but still populate it with data. For example, perhaps a flag as to whether or not a product is appropriate for a variety of ages. And they will change the meaning of that field very helpfully from maybe, say, an integer to a string. And now your integer comparison, oh dear. And it will go poorly, and that will be great. And yeah, okay, so the main thing here is please check your data. Maybe also one day they will come in and delete your training data. And then you'll have like, 200 records or something, and you'll train a really high quality model for those 200 records, but it might not quite be as good as this one you trained on like 10 million records. And okay, there's a bunch of tools you can use for validation. You should check your cross-validation performance. You should check if your model all of a sudden starts to converge really, really fast or really, really slow, because something is probably bad. So check these things as well. And don't deploy automatically without doing a shadow run to make sure everything isn't going to catch on fire. And now we reach the second most important slide, which is, these are some books on Spark. I have not written all of them. And so that is why we will go to the most important slide, which is the most recent book I wrote. It is almost completely unrelated from machine learning, but that should not stop you from buying several copies of it. If you buy the print copy, it comes in a box, which your cat will love. And if your cat pees on the book, Amazon will not let you return it. You don't actually have to buy my book, but if you do want to, it's about how to make your Spark code run faster. And there's a tiny little bit of it about how to debug your Spark code, because normally when you start making it run faster, you start making it fail. Oh well. Oh yeah, if anyone really wanted to go play around with the code and try things besides fitting a decision tree, there's Scala and Python notebooks in there, and it leads you down a few different paths, and you can go and play with them and hopefully do something fun. And that's pretty much it. Okay, thanks, bye. justifying my expense reports.